Hi, welcome everybody to the first of the fall UCLA Communication Systems Laboratory seminars. And we're really happy today to have with us Riccardo Schiavone, who is coming to us today from Italy, somewhere geographically in between his two institutions of the Polito, the Polytechnic University in Torino, and DLR. We're really excited to have Riccardo, who has recently completed his master's degree, tell us about his master's degree work, which is on convolutional codes with an outer CRC, something that our research group is really interested in, and the analysis of their ensembles and performance under some list decoders with bounded list size. So Riccardo, I have given you permission to share your screen. And so we'll just let you take it from here.
Thank you, Rick. Tell me if you can see anything or not.
What we see yes, it's beautiful. We can see your slides.
Oops, spoiler. I think now you can see better.
It's perfect. Yes.
Okay. Okay. Today, as Rick said, I want to talk to you about the performance analysis of convolutional codes with outer cyclic redundancy check codes. It will be, let's say, a short talk. I know that many of you know a lot about it because it is of interest, especially at UCLA, this concatenation. What we'll discuss will be a brief introduction about why I decided with Gianluigi to focus on this topic during my master thesis. Then we'll briefly talk about the serial concatenation, and I'll show you some interesting tools to study ensemble of codes, and an important tool to study performance of both the ensemble, but in general of linear codes, not only linear. And then we'll discuss about some decoding algorithms, two in particular, and then at the end we'll conclude with some results and conclusions. And if you have questions, of course, you can interrupt me whenever you want, or we can even do them at the end. For me, it's fine both. Let's start. The main motivation why we decided to study the performances of convolutional codes is because they are very good short codes, and their performances are even better if given that the memory is larger of the convolutional encoder. But the problem of the memory is that larger the memory and more complex is the decoding of these codes if we use some particular decoders. An interesting thing is that the concatenation of convolutional codes with other linear block codes, with outer codes, it allows to obtain the same performances while decreasing the memory required, so decreasing also the complexity. And a really recent result that is from the group at UCLA is that it is possible to find efficiently the best degree M outer cyclic redundancy check code that can be serially concatenated to a specific convolutional code. And this was the starting point of the thesis, because this efficient implementation allows us to really create things, and we'll see them. But why the interest in short codes? Because, for instance, in IoT systems, we have the main goals are to the main constraints also are that we have a lot of sensors that are placed nearly everywhere. And for instance, in a satellite network, that can cover a lot of a gigantic area, it means millions, billions of devices that communicate and send their data to this satellite. But there are constraints on these devices because their memory, their battery has to last 10 or even more years, because these devices are placed in remote areas or areas which are difficult to be accessed. So we don't want to replace their battery continuously. Moreover, an important aspect is that these devices are just sending few bits of information, like can be the position or or an information about the pressure or the particle per millions of carbon dioxide. So just few information, so few bits, and so we will not see long messages that will be sent through this channel. At the same time, we still want to have reliable communications, and this is really a great constraint, for instance, in these systems. Why I say that this is a great constraint? Because theoretically, the best we can do, the best we can do in performance is bounded by the length of the packet and the redundancy and the rate of the code we are using. Okay, and if you see here these blue and red lines, they represent the theoretical bound. So the best we can do with codes of certain lengths for a rate of rate 1/2. So when the redundancy is the same amount of the information. Okay.
Riccardo, we have some new people here who are new to some of the stuff that you're talking about, and I think they would appreciate it if you go ahead and tell them what those acronyms mean for the two bounds and the approximation.
Okay. This the blue curve you see here is the random coding union bound that is developed that is an achievable bound, and it means that we can achieve this performance. Okay, this blue curve there exist some codes that can perform with these error correction performances here, while the red one is the meta-converse bound that is a lower bound, so we cannot do better than this at all. We don't know if there are any codes that can perform with these good performances. Okay, and so when we analyze codes, these tools are really useful to tell us how good are our codes and our decoding algorithms. Because if we have a code that has length 128 and with 64 information bits, so rate 1/2, and we are close to the blue curve, we are really happy, because it means that we have very good codes. Okay, so and there is also no meaning in trying to do better. Probably we should focus on doing on having the same performances, but with less complexity. Okay, so this is also interesting these are really important tools. Okay, for that to be used in the channel coding analysis. Okay.
Thank you. That's really helpful, I think. Yeah.
Riccardo, this is Doris Schlipsaler. Your performance, the dash one seems for the 128 crosses the red one.
No. These are not the performance of my. The NA is the normal approximation. That is an approximation.
The Polyansky's normal approximation.
I think it's the Polyansky one. Yeah.
Okay.
But it is another interesting bound that we can use to understand how good are our performances. Okay?
Yeah, which uses dispersion for IT wide Gaussian nose channel.
Yeah. As you can see, of course, these performances, the best we can do with short packets is much worse than the best we can do with longer packets. Okay, So it means that at least we want to do the best we can. Otherwise, we are wasting energy. Okay, and this is crucial, especially in systems where in IoT systems where the sensors are really cheap and we want the battery that lasts over 10 years. And at the same time, we want reliable communication. So we need to pay also energy to reach a certain target of reliability. Here is the code word error rate that I think everybody is familiar with or not. I think yes.
Yeah, I think we're good.
Okay, and here in the x-axis, there is the energy per bit over the noise. Okay, so it's a measure where it's the energy of the information bit. Okay, because there are different ways. SNR, energy per bit over N0, they are only proportional. So there is the curve. If you use SNR, are only moved in this diagram, but I mean it's just it's a proportion to pass to move from one to the other. Okay, so but here we refer to the energy to the information bit.
Excellent. Thank you.
Just to be clear. Okay. Let's speak about the serial concatenation. I hope everybody is familiar with cyclic redundancy check codes and convolutional codes. If anybody have doubts, because I thought everybody knew a bit about them, so I have skipped in the introduction. For instance, data encoders and other stuff. So if anybody has doubts, I have other presentations in which I have in case it's needed. Okay, so feel free to ask questions if you have no idea what they are. If you are familiar, what is the serial concatenation we have taken into exam is made of an outer code that is the cyclic redundancy check, and an inner encoder that is the convolutional encoder. So we have a message that is encoded via the cyclic redundancy check code. It produces another message that is the input of the convolutional encoder, which produces the final code word that we use. And the cyclic redundancy check used in this concatenation is the best degree M cyclic redundancy check code for the convolutional code that is used and taken into exam. And here you see the references about how to find the best degree M cyclic redundancy check code for a specific convolutional code. As you can see, the main idea also in these papers is how to use efficiently then the outer encoder. It is first, let's produce a list of possible good candidates of messages that can have been transmitted. Okay, we're using a list decoder, a list convolutional decoder based on can be based, for instance, on Viterbi. In this code is based on Viterbi, and we'll see it briefly. And then from this list, let's apply let's see from from our list. Let's see if all these messages also respects the parity equations of the cyclic redundancy check code. If it is so, okay, we choose the best among them. Otherwise, we declare an erasure if there are no codes that also no messages that also respects the parity equations of the cyclic redundancy check code. So this was
you find your list. You find all the code words on the list first, and then pick the one that's highest on the list that has the CRC, or do you find the best one and then the one after that?
We'll see that there are two ways of building this list. One that is in a serial way, and the other all in parallel, and then do our selection. So yeah, here is just to say that the main idea of the decoder will be having a list decoder and the CRC that will expurgate the list and will tell us if it's okay or not, the message. Okay.
Yeah.
I see maybe some messages in the chat.
Well, just John Luigi is giving us a reference to one of Darius's papers on bounding code performance for short block lengths.
Okay, super. Thank you, Gianluigi. Let's see now. Oh my God, where I am? Okay, yeah. Let's see now how we can, for instance, study the ensemble of codes that have that use this serial concatenation, but we decide to place in between the outer encoder, the CRC, and the cyclic and the convolutional encoder, a random uniform interleaver. So the bits from the bits that we have at the output of the CRC are they are placed randomly somewhere else and then sent to the convolutional encoder. Okay, and how we can study the performance of the ensemble in general to understand how good is to place or not a random interleaver. This is really important to understand if it makes sense or not to place a random interleaver. And why to use, for instance, a random interleaver? Because with convolutional codes, random interleavers have proven in past to be really effective to enhance the performances in concatenation of convolutional codes. But in this concatenation, is also that powerful or not? We'll see in few slides. Which are the ingredients to study in general a serial concatenation? We need the weight enumerator of the outer encoder, that is the number of code words that have a certain Hamming weight. Okay, and how can we find it if it is, for instance, a cyclic redundancy check code? Luckily, it is a high rate code, so we can use, for instance, we can study its dual code, and then use some mathematical tricks to recover the weight enumerator of the CRC. But for us, it's important that there exists a way to find it. And then we need another ingredient that is the input-output weight enumerator of the inner encoder of our convolutional code. What is the input-output weight enumerator? It is not only telling us how many code words have a certain Hamming weight, but it is telling us how many code words have a certain Hamming weight, given that the input message has a certain another Hamming weight. Okay, maybe it's confusing a bit, and we need these two ingredients to find the average weight enumerator of the ensemble. But it is not sufficient only these ingredients. We still have to place our interleaver in the equation. And it is, since we said that's uniform random interleaver, what it does, it takes the ones, so the ones that are the ones of the code word at of the outer encoder, and it places them at random. So if we have if our code word of the outer encoder has n out bits and only W are ones, all the possible combinations of these ones are n out choose W. With all these ingredients, we need, of course, to remove the W, the number of the Hamming weight of the outer encoder from the equation. So we do a summation, and this can give us the average weight enumerator of the ensemble of a serial concatenation. Okay, so this equation is always valid for the serial concatenation when the interleaver is a random uniform interleaver. So this average weight enumerator is telling us the average performance of all the codes, all the possible codes, all the possible random, all the possible interleavers that we can place here. So it's just an average, okay? It's not a specific one. This is important. And so another important thing is that we can expurgate from this ensemble codes, those codes that have a low minimum distance, a distance that is lower with respect to the one of the average weight enumerator. And how to do this? Let's see with a very simple example. Let's imagine that we represent the average weight enumerator of our ensemble using the average weight enumerator function, okay, where it is simply a polynomial where we have as coefficient of the degree k term of the polynomial the average weight, the number of code words with that Hamming weight, okay. And in this case, let's it's usually I mean, if you try with codes, you'll see that ensembles do not have integers here. Okay, so it's not an integer number of code words, but because it is the average of many of all the weight enumerator. So here we don't have integers, but this is good because Gallagher showed a way to show that it's possible to remove the bad codes when the numbers here are smaller than 1. Okay, because intuitively, which is the idea, it is that among all the codes here, there are some that have less than one code words of Hamming weight 5, and there are others that have Hamming weight 5. So it means also that there are codes in this ensemble that have a minimum distance that can be, for instance, 6 or 7. How to find easily the unexpurgated ensemble? It is summing all the terms except the degree 0 term up to have summing all the coefficients up to have a number which is greater than 1. The first time we have a coefficient greater than 1. So for instance, in this case, if I sum up to the 4th term, I have 0. Then if I sum also the 5th, I have 0.5. If I sum also the 6th coefficient, I have 0.7. And if I sum also the 7th, I have 2.6. So now I have a coefficient that's greater than 1. So it means that I cannot have any guarantee that there are codes that have a minimum distance greater than 7. Okay, but I can guarantee that there are codes that have a minimum distance of 7. Because 0.5 plus 0.2 is still below 1. And here are this is what this formula is saying, okay?
Riccardo, this is based on the average. Is it possible to find the variance? How much deviation we have from this average, especially for the short blocks, based on uniform interlevers?
That's an interesting question, but Gianluigi?
Yeah, because if the block size gets very large, therefore, usually variance based on the Gallagher's, Shannon, and so on, everything, the deviation goes to 0. But for short block, it's nice to have, the variance in order to see that how much deviation you may get.
I agree. I don't know.
I know that it's part problem, but maybe it's possible.
Yeah, I don't know. I have no idea if there are any tools that can be used. Or
I haven't seen anybody consider variance, but again, this is something to think about.
I agree. I mean, it's interesting to understand what we can do. Yeah, but I have no idea if there are any theoretical tools that can be used for this. I don't know if Gianluigi, if you're listening us, if you know anything.
Yes, yeah. No, it's a very interesting question. I know that for linear random ensembles or for random ensembles, there have been works studying the variance of the weight of the weight enumerator. Sorry, But for the case of serial concatenations, I don't know much. But it's very interesting and probably something we should look at, Riccardo.
I agree. Okay. If there are no other questions, I continue, but thank you for the point. And let's have a look at an important tool that to study the performance of the ensemble and also in general of codes. Okay. We know that upper and lower bounds are important tools, but some are better than others. Not all upper and lower bounds are tied to the real performance of our codes. And what I suggest you is this book from Sazon and Shamai, and that is that I placed in the references, and it's really good. There are are presented many upper and lower bounds with all the derivations step by step. It's really super. I suggest you for your life. Because all of us have the habit, have seen a simple upper bound during channel coding lectures, okay? But we can do better than that upper bound, and the key equation to do better than that is based on this simple upper bound, where the probability of error is can be upper bounded by the probability of errors while the received vector belongs to a certain region, plus the probability that that vector that does not belong to our region. Okay, and this second term is dominant at low SNR. Okay, when the noise is prevailing, and this the second term is not present, for instance, in our classical upper bound that is usually taught during channel coding lectures. What we can see here is that what influences the results of the tightness of these bounds to the real correction performances of our codes is the choice of this region, and some regions are better than others. Okay, one of the best upper bounds that we know that has proven to be really tied to the performances of codes is Poltirev's tangential sphere bound, that is based on using as a region an n-dimensional circular cone with alpha angle theta, and whose central line passes through the origin of our n-dimensional sphere and the transmitted signal. Let's have a look with an image, because otherwise it seems really complex. Here is the origin, here is our transmitted signal, and here there's another signal that belongs to that we can have, and it is a signal belonging. It is a signal was code word is a distance k. It is a Hamming distance k from the code word of our transmitted signal. Here we see the alpha angle theta, and here we see the half dimensional cone, the half and dimensional cone, and what does let me rephrase. Which are the most important things to derive our bound? Are this radius r that is optimized? I don't know if you can see, because it's maybe it's if you want, I try to zoom. If you cannot see letters or other things, tell me.
No, everything's fine. Yeah.
Okay. Okay. We have this radius that is optimized, but if you try to do the derivations, the radius is the best radius does not depend on the signal to noise ratio, but it depends on the average weight enumerator of our code. That's really nice, because otherwise it would have been really a mess to every time find this radius. But we can find it so offline. the best radius. Here you see Z1, that is a noise component. It is the radial noise component from our transmitted signal to the origin. And then we have another noise component, the Z2, that is orthogonal to Z1, and it is in the plane of our transmitted signal, the origin, and the signal from the code word at a mean distance k from our transmitted code word. And what it is important is that, as I said before, in our equation, we have to understand when our received vector is inside the region in an area in which we decode it wrongly, okay, with a maximum likelihood decoding approach, and when we are outside this cone. And if you see here, this area of the cone from between this RZ1 and this BKZ1, okay, this triangle here, you see that if our transmitted signal is here, a maximum likelihood decoder will assign it to the to signal SI, okay? So we need to understand to compute this area. This is important inside, okay? And I will not do with you all the derivations, but it's just to tell you what this strange equations is telling us. It is telling us that there are some components inside this tangential sphere bound. One that is that is the case in which our noise is that strong that we are outside the cone. This is the component that's telling us that we are outside the n-dimensional cone. This is in the second line there is the term that is telling us that we are inside the cone, but in that small area that for which we decoded wrongly. Okay, you see that there is here the BKZ1 and the RZ1. Okay, and of course, we need to integrate among all possible values of Z1, that is a noise that we are assuming Gaussian. This is the probability density function of our noise component. And this last term outside of the integral, it wasn't considered in the first version of Paul Tirep's tangential sphere bound. It's just a case in which the noise component here, it is that strong that we are on the other side of the cone. Okay, but it's also, if you don't use it, this is a really minor contribution. Here, this gamma is because this gamma is the incomplete gamma function to approximate the areas of key distributed random variables. But I will not enter in the details. All the possible steps are well explained in the book I suggested you before. But it was just to tell you, to give you an idea of this bound. Okay, it seems weird, but it's really well explained.
Riccardo, in the previous slides, the bond that you have shown that you said by Sasson and Shamai, actually, in 1963, Gallagher proposed that.
You mean?
Yeah, this one.
Okay, yeah, the general, yeah.
Yeah, but then the Sasson, the Shamai used that. I also used the same bound later on.
Yeah, but there are many versions also of tangential sphere bound that appeared during time.
Yeah, but this equation that you wrote here is originally comes from Gallagher.
Okay. Thank you. And so yeah, and this is the crucial equation if you want to discover new bounds, new tight bounds, you have to choose a new region, and you can maybe discover new interesting bounds. Just to show you.
Yeah, I put another reference that I discussed about this Gallagher bound and the work of Shamai and Sasson. But there are some more details on that, especially the reference that I provided doesn't require any kind of integration or optimization. But
Okay.
it obviously is not as tight as these bonds.
Okay, thank you. Thank you. Just to give you an idea of the power of this bound, this is the conventional upper bound. That's the classical union bound that is taught in channel coding lectures. And this is this one is our tangential sphere bound. And as you see, it's really close to the performance of the code, also at lower values of EB over N0. Okay. And this is for a certain, this is for a rate 1/3 turbo code. But let's have a look on how to use it in our serial concatenation.
Well, okay. I guess I'm still that previous chart.
Sorry.
Oh, okay. So the pluses are simulated codes with different numbers of iterations.
Yeah, sorry.
Okay,
Yeah.
so we only need to pay attention to the most iterations, and even that, there's 10 iterations, so you might do better with more iterations. And
yeah. Here
so
is
the best bound is the tangential sphere bound, and there's a place there where the 10 iteration code is not even, still above the bound, right there, yeah, that little banana. But that just, if you ran for an infinite number of iterations, then you can be confident that you would be below the bound because it's an upper bound. Is that correct?
Yeah.
Okay.
Although
Okay,
the upper
great.
bound is on maximum likelihood decoding, instead this is an iterative decoder. So
Oh, so really
Yeah.
you don't know. Okay, yeah.
yeah.
But that's the neat thing because we're about to talk about list decoding, which if you use an infinite list size is actually ML. And so these bounds would really apply.
Yeah.
With a large enough list. Okay, great. Thank you.
And
sorry to slow you down. Keep going.
Okay, let's have a look, for instance, on our case using the best degree 6 convolutional, CRC code for the distance spectrum optimum tail biting convolutional code of memory 5. Okay, if we try to study the performance of the ensemble and the expurgated ensemble, are these green and blue curves here. Okay, while if we try to decode, for instance, our code without using any interleaver at all, okay, and using a serial list Viterbi algorithm, and we'll see briefly what it is, with a large enough list, and we also try to plot the performance of this code using the tangential sphere bound, using the first terms of the weight enumerator of this code that we can compute using a well-known algorithm, okay, from Young, okay, and you see that we can do better than using an interleaver. So it means that this concatenation is really strong also without the need of any interleaver. And this, if you try to do it for also other cases of convolutional codes and other CRC and other degree of CRC codes, you'll see that we can always do slightly better or even much better, like in this case, okay? And that's a really interesting result, for theoretical result for these codes.
So what you're saying is that we don't need to put an interleaver between the CRC and the convolutional code.
For these short codes, no. I agree that there's no need for it.
Now, but the pink curve is better.
It's for random codes, yeah.
Any random, but you haven't. But I guess I feel like if you were going to you could increase your V and your M and get closer to that random pink curve, right? Yeah.
I've not shown here, but as we said at the beginning, increasing the memory of convolutional codes, but also increasing the degree of the cyclic redundancy check codes. These curves, these blue and green and this red curve, they get always closer to this pink curve that is one of the bounds that tell us how good is a code, okay, if we are really good or not, okay?
But the random codes, oh, I'm sorry. When you say random codes, is that a meta converse or a random coding union bound, or it's just which one is that?
In this case, it is close to the random coding union bound, but it is based on the tangential sphere bound. So, but it's really close. If you depict it with the random coding union bound, they are really close. So,
okay. I guess
another...
that's a whole different thing then, that you apply the tangential sphere bound, not just to the convolutional code, but to the random code. I guess you were telling us about that, assuming a, wait, that wasn't assuming a random interleaver. Did you tell us about this pink curve?
No, I didn't do it before, but it's not for the case of random interleaver. It's really for random codes in general.
Got it. Okay, I'll stop slowing you down, but thank you. So at least, you see that you have some, between Darius and me, we're keeping you busy. Okay.
Yeah. Okay, just briefly, let's see some decoding algorithms. We all know Viterbi, I hope. Yes. Which are possible list decoding algorithms that are based on Viterbi. The easiest one is the parallel list Viterbi algorithm. That is like Viterbi, but instead of having only one path at each node and update that path with the distance of the edge, and then choose at the following node, at the C node in this case, the best between the incoming path from node A and node B. We have a list of the best paths at node A, a list of best paths at node B, and what does C node is simply choosing the best L among these two L paths. Okay, so this is a very simple idea, and we'll see later how good it is later, but not that long. But we'll see soon. Another idea is the serial list Viterbi algorithm, that it does not give us all an entire list at each step, but it does another thing. It is based on a very simple idea, and it is that from our best path, the possible the other possible paths, the possible local best paths, have to leave it once and rejoin it in another time. Okay, and what we need to do is to find all the possible local best paths at each section, at each trellis section of our best path, sort the entire list and choose the best. Now, depending on how we manage this list, we can we have different serial list Viterbi algorithm. Okay, but what we do is at the first iteration, so after having found all the local best paths, and if we choose the best, we have the second global best path. And if it's, for instance, if the best path was not okay for the cyclic redundancy, it didn't match the parity equations of the cyclic redundancy check code, we can say, okay, so let's have a look at the second global best path if it matches the cyclic redundancy check parity equations. And so we can find the second. Then from the second, if it's not okay, we can have a look at the local best paths to the second global best path and insert them in the previous list that we had before, choose the best among all, and this will give us the third global best path. And if the third global best path is not enough, we can go on and on, okay? Now, the list, it's if you want to have a very fast algorithm, must be handled with a data structure that allows you to have a logarithmic complexity in insertion and in deletion. Okay. Last algorithm that we'll briefly see is a very efficient suboptimum algorithm to decode tail-biting convolutional codes. I don't know if all of you knows what are tail-biting convolutional codes. They are those convolutional codes that have an important constraint at the encoder, that is the transmitted code word. It starts from a certain state, if we look at its path in the trellis, and it ends in the same state. Okay, So, for instance, this blue curve, this blue path here is not a tail biting path in our trellis, okay? And a very simple idea to decode tail biting convolutional code, since we don't know the decoder from which state the encoder started its encoding. We need to do what follows. We run simply Viterbi. If the maximum likelihood path is tail biting, we are happy. For us that path it corresponds also to a transmitted code word and a transmitted message. Okay, if it's not the case, the values that we have found at the end, the path metric that we have found the last states, we use to reinitialize our states at the beginning, and we rerun Viterbi using the new starting points. Okay, and if in this case it is our maximum likelihood, our best path is tail biting, we accept it. Otherwise, we can repeat the iterations. Just to tell you, usually 2 iterations for codes of length 12864 are more than enough. Okay, this is just to tell you about this WAVA. Now, can we combine the previous algorithms together and see how they perform? Let's have a look about them. And it is, for instance, that this is, I'll show you just for one possible combination of tail biting convolutional code and cyclic redundancy check code. But of course, there are online, you can find, for instance, my codes in which you can try other cases, okay, the cases you like. This case, it's using a tail biting convolutional code of memory 6 with its distance spectrum optimum cyclic redundancy check code of degree 6. Okay, and as you can see, these dotted dashed lines, they represent simulations when we are using a parallel list Viterbi algorithm with a certain list. The green one has list 1, while the blue one has list 16. And you see, increasing the list, of course, our performances are improving. That's something good. But these solid lines instead are simulations results using WAVA, the wraparound Viterbi algorithm that we saw in the previous slide, and after the reinitialization of the values at the beginning, we run the parallel list Viterbi algorithm. So just to be clear, we run Viterbi, we reinitialize our values at the beginning, and then we run, instead of the classical Viterbi, the parallel list Viterbi algorithm that we saw before. And as you can see, using WAVA plus the parallel list Viterbi algorithm, let us reach with the same list much better performances. Okay, we see here that the gain is important. And already with a list 16, we obtain the same performances, nearly the same performances of a tail biting convolutional code of memory 8. Remember that memory increases exponentially the complexity of the decoder. So this is a really interesting result. And what happens if we use a serial list Viterbi algorithm at the decoder? We have to say that don't be scared about the list size, because the list grows. Because as we said before, we are using logarithmic complexity to build this list, so it's not huge. Moreover, the decoder may not use every time a list of 512, but as we saw before, first it uses list 1. If it's not okay, it finds the second path. If it's not okay, the third, and so on. So this is the maximum that I decided to allow for the decoder. Okay, and we see that with list 512, we have more or less the same performances we had with list 16 and the parallel list Viterbi algorithm. But as you can see now, these dotted dashed lines and the continuous lines, they're not that different. So it's suggesting us that the use of the wraparound Viterbi algorithm with the serial list Viterbi algorithm may not be that effective with the serial list Viterbi algorithm. This is the same code, okay? Just different ways to decode it. And just to have last comparison, these are the comparison of different tail biting convolutional codes with different memory. You see, increasing the memory, we are getting closer to this black line, to this dashed black line that is the random coding union bound that we saw at the beginning. And we can be competitive to other codes that are present, that are, for instance, standardized in 5G, like the polar codes. Here are decoded with successive cancellation list decoder. Okay, and as you can see, increasing the memory, depending on the memory we choose and the degree of the CRC, we can do at least at least good as with polar codes, or even better in some cases. Okay, so also this is really interesting. Okay, and just to conclude, so we showed that we can decrease the memory of the convolutional encoder if we concatenate it with a cyclic redundancy check code, because we saw with results. We saw that the wraparound Viterbi algorithm helps in decreasing the list size, or better, for the same list size can give us better results for if we use it with a parallel list Viterbi algorithm, but not with a serial list Viterbi algorithm. And we see that tail biting convolutional codes with cyclic redundancy check codes, they are really competitive at short block length. The one problem that I've not shown you, but if you try to play a bit with these decoders, you'll see that the list size it increases exponentially, while if we increase the degree of the cyclic redundancy check code that we use for a specific tail biting convolutional code. And this probably, especially for tail biting convolutional codes, it's due to the fact that at the decoder, if we have a look at the trellis, as we saw before, we have also non-tail biting paths, and there are many non-tail biting paths in our decoder. Okay, and those they are in the lists that we create, and so this is really what it is penalizing tail biting convolutional codes from that aspect. Okay, so it is preventing us to use too large values of the too large degrees of the cyclic redundancy check code. Okay, this is all from my point of view. I hope everything was clear or not that confusing.
Oh, it's great. Thank you very much. Can we go back and look at your last plot again?
This one with the comparison with polar codes?
Yes. So can you remind me, are you doing parallel or serial list Viterbi decoding in this plot?
In this case, I've used the parallel one. Okay.
Okay, and so I is the number of times you do the WAVA in the legend?
Yeah. Sorry for not explaining that, but yeah, I is the number of WAVA iterations. So we do simply I equal 1 means that we have done only Viterbi, so no wraparound updates. I equal 2 means that we have done an update and then we have run the list decoder.
Great. Yeah, I've heard that from other people, including Ethan, that adding a WAVA step definitely helps with the complexity. But okay, so let's open it up now for questions. I mean, do you think that, did you try to go further, like than V equals 8?
Yeah, I don't have
CRC4, right? You got a 4-bit CRC and an 8 memory element convolutional encoder as sort of your best performance so far. Have you tried, would you get closer to the RCU by adding another CRC bit or adding another memory element?
Yeah, of course, I have also other results, but I decided to put these ones only because here the list size is small enough to be competitive with other decoders, like the ones like the successive cancellation list decoder for polar code. So,
do you have a sense of the complexity between, for example, the green and the pink curves, like how much runtime you took?
No, not in this sense, but it was just about the problem that both algorithms are using sorting networks in hardware, and sorting networks, they increases the area occupancy based on the list size, okay? Because they have to sort a fixed number of elements, and so also this plays an important role in from the hardware implementation perspectives. So it was more based on that. Sorry to be.
No, it's great. I think it's something we're really interested in. And another one of our researchers, Jacob King and Lexi Kwan, are running a bunch of simulations of polar codes and 5G polar codes, and then CRCs with convolutional codes. And we're actually tracking the time on the laptop for both implementations. And I'll send you this plot that we're making that sort of like as you increase the list size or as you change the SNR, the time to decode changes and the performance changes. It's kind of fun. So I'll send that to you guys later. But let me open it up. Do we have any questions from our audience? You can just go ahead and raise. Why don't we stop sharing and go to gallery mode? Oh,
wait. I have a question.
Go ahead, Bill. Yeah.
I think on the next slide it was, you talked about increasing the degree of the CRC, Riccardo.
Yeah.
It ended up exponentially increasing. Let's see, can you go to the next slide? Or
yeah, give me once. Okay. Yeah.
Let's see. Yeah, the last bullet.
Yeah, I have not shown here, but both if we use a bounded list size to try to reach a near maximum likelihood performance with both the parallel list Viterbi algorithm and the serial list Viterbi algorithm, we see that the list size to reach it we using a bounded a maximum allowed one, it grows exponentially to with the degree of the polynomial used as a cyclic redundancy check outer code.
Yeah, I have to think about that. I'm not sure I noticed that. Do you know, Rick? Did you notice that?
I know what he's talking about, but the non-tail biting codes, well, actually adding the CRC, it depends on how you think about it. I mean, we like to think about like a certain block length message. And then if you add to the CRC size, you think about the CRC eating into the message bits. Then if you have that perspective, the number of non-tail biting paths doesn't change. But if you leave the message size, if you sort of let the message grow with the CRC, then you are going to get more tail. The total number of convolutional code words is just growing. Do you understand that distinction, Riccardo?
Not sure.
But it is a problem. The non-tail biting paths are that's kind of the thing that makes doing list decoding and tail biting decoding hard. But I keep thinking that there would be a way to sort of think about a tail biting code as actually a code that started, new or V bits earlier from the 0 state, but you punctured all those out until you got to the state that you're at. And in that sense, we might be able to kind of think of a decoder that can exclude those non-tail biting code words earlier. It's something we're looking into. I think it's a very interesting problem.
Yeah, because for instance, 0-tail terminated convolutional codes, the list, yes, it grows, but not with the same rate, because it grows, but not that dramatically, I saw.
Anyway, Bill, I think your question is something that's open for us, and it is something that we could all work on together.
Yeah, in my simulations, I didn't notice that. I'm not saying it doesn't happen, but so it increases exponentially for the same code word error rate. Is that what you mean?
I mean, yeah, to reach near the near maximum likelihood performances, I saw that I have always to increase the list size, and it
Okay.
grows a lot.
Yeah, now I think I'm getting it. Okay, thank you.
Riccardo, is there, have you measured undetected error probability of these codes?
I have somewhere some studies on undetected error probabilities, but I have to say that now I have to search them. If you want, if you're interested, I can send you some results, yeah, about them. But you can also find, for instance, with the serial list Viterbi algorithm, also Rick, Ethan, they published also those the undetected error probabilities of these codes with the serial list Viterbi algorithm in some of their papers. So
yeah. Also, have you compared with you put polar code? How about the LDPC code? I guess Gianluigi already did lots of work on the short blocks, so he knows most probably much better than me.
No, Darius is the king in this. So I think we should definitely compare with some of the codes also that Darius has been working on in this regime.
But I also think that you have that paper with Coxon that compares with like a ton of short block length codes originally. Do you know what I'm talking about, Gianluigi?
Yes, the paper with Mustafa. I think it's the paper together with Bill as well.
Yeah, Bill is on that paper, right?
Yeah.
And there were tons of codes that were compared, and then we sort of used that. I think, but I think the answer is that since we're comparing with the RC, when you compare to the random coding union bound and the meta converse bound, and you're close, then sure, there might be other codes that are also close, but nobody's going to do better than the meta converse bound. So I think it makes it a little easier to be confident that we're doing things right.
I mean, I have the feeling that as soon as we move away from the very short block length regime, so 128 and 64, which is what has been used for many simulations here, when we start to get into 256, 512, then, for instance, non-binary LDPC code starts to close the gap and get quite competitive. But I would say probably one is to really go to those block lengths in order to see low density parity check or turbo codes to approach tightly the performance of polar codes with SCL decoding or convolutional codes with least and outer CRC. So I think for very short blocks, so 128.64 is really hard to beat these codes.
So do we have any other questions? Any questions from our from the graduate students and the undergraduates?
No, I have another question from Riccardo. Sorry that I'm asking too many questions.
No, you're not. It's great.
No.
we are here with you.
Is it true that, for, using convolutional code and CRC, usually you choose for the given code parameters, you choose the best convolutional code and the best CRC? Is it combination best and best is always the best?
Let's say the algorithm let you find the best degree M cyclic redundancy check code for a specific convolutional code. So you compare all the possible convolutional codes with all the possible best degree M cyclic redundancy.
Oh, so you
code.
did that? You already done that?
No, because it's
Yeah.
huge. Because you should check.
Yeah, but it's good to know that best plus best results in the best.
That's an interesting question. I don't know if at UCLA you also checked it or not.
No,
but,
we haven't checked that yet, but there is a couple of things that one can do to make progress on the question that Darius is asking, which is, how do I know if I could have done better by taking a convolutional code that at first blush might have looked worse, but with the right CRC ends up being better, which is certainly a possibility. You can bound the benefit that you can get with the CRC by looking at so if you look at your convolutional code's weight spectrum, and it's kind of related to Gallagher's trick, about sort of collecting up things from the ensemble weight spectrum. But now we're talking about the weight spectrum of a single code. The CRC expurgates code words out of that weight spectrum. And we know exactly how many code words it's going to expurgate away. It's 2 to the CRC size. So for any convolutional code, the best joint performance you can get is if it expurgates away all of the closest code words. So for each particular convolutional code, there is a bound on the best that you could do based on the distance that lies that deep into the distance spectrum. I'll stop here for a second. Riccardo, is what I'm saying making sense to you, John Luigi?
Yeah.
Okay, so in this way, if you were to go through all the convolutional codes, you can, for each one, give, this is the best I could possibly do with a CRC. And so when we use our standard approach and we take a convolutional code that has the best weight spectrum, and really probably has the best value of this bound, then we get kind of close to that bound with our CRC design. Then any code whose bound, the best distance I could get is a smaller distance than the one I've already got, it's out of contention. And in this way, if one really wanted to tackle the problem at another level of optimality, I believe that that the complexity is reasonable. You'd end up with a small enough number of convolutional codes that you cared to look at that you would be able to find it. And maybe you'll be able to shave off, actually improve the distance by one notch, or improve your neighbors. Because there's no reason to believe that finding the best convolutional code and then finding the best CRC for that code is absolutely the best joint construction. But we think it's probably pretty close. So sorry, I guess I answered that's my feeling about the answer to that question.
I share the vision. I agree. It makes sense. Yeah.
I wanted to comment on Darius's earlier question about undetected error rate. And Rick, you can correct me if I'm wrong, but like Rick, in your curves, when you come very close to the random coding union bound, you use list sizes of 1,000 or 2,000 or 5,000. And so the probability of undetected error there is really close to 1. Right, and in those cases with really
well, when you say it's really close to 1, what you mean is that all the errors you're making are the undetected errors. Right, because if you have a list, basically 2 things can happen, right? With list decoding, you either don't find a code, so you have a negative acknowledgement, or we call it we call it a knack, but you could call it an erasure. Or you think you found the right code, but you just went so deep in the list that you found a wrong code that happens to match the CRC, and that's the undetected error. And I agree with you that, when this thing is working really well, that's all you got are undetected errors. So the error rate is the undetected error rate.
Yes.
And I've also the sense that using the wraparound Viterbi algorithm may increase the undetected error rate, because it can do what you said before. You choose something that in the list was below, and so there's also the risk of choosing something wrong because you change the distribution.
Well, actually, there's a general question that I'd like one of my graduate students, Alex Baldauf, is going to be looking into, which is you could think about the list size. Right now we sort of think of, well, the best list size is infinity. But if you think about, as you go deeper into the list, what's the probability that I'm going to find the correct code word if I just look more deeply? Or what's the probability that I'm actually just going to find a random wrong code word that happens to match the CRC? I believe there's a list size that's less than infinity where you should stop. because the reliability of what you're doing gets so small. And we're especially interested in understanding that list size, for example, to decide when to go ahead and, like, if I go deep enough into the list and I haven't found a code word, rather than going deeper into the list, I just send a knack and get some more incremental redundancy that would allow me to do a better job of decoding. That's where we would like to go with that question. But, oh, I noticed that I'm talking too much. Do we have any questions, any more questions for Riccardo?
I think I have a question. So
Go ahead.
I just want to ask Riccardo about whether you know that we also submitted our journal paper this year, and we also designed the good CRC for the TVCC, because in the past we don't have a algorithm that can do this. So now we have the complete table of best CRCs for the both ZTCC and TVCC.
Yeah. I saw both the paper you submitted in 2020, if I'm not wrong, and also the transaction. It was,
I think I submitted the preprint in April this year.
Yeah. Gianluigi sent me the paper. Yeah.
Great.
Yeah, thank you. Yeah, it's very nice job. It's very nice work. So yeah.
Okay, thank you.
No, thank you to you, because you did something brilliant. So,
well, Riccardo, thank you so much for speaking with us. And we'd love to stay in touch with you and think about things that we are both interested in the same things. And I think there'll be a lot of fun things for us to do together. So maybe Gianluigi and you and I can touch base on that going forward. But I just like to, now we can go ahead and go to gallery mode and let everybody turn their cameras on, and we can give some virtual applause to Riccardo for his excellent talk. Here, I'm going to turn this thing on. There we go. Thank you, Riccardo. Thank you. It's a pleasure having you. Thank you, Riccardo. Off speaker. Okay, so now I'm going to go ahead and stop the recording.